Hi everyone, my name is Astrid, and today I'm here to talk to you about our work called Robust Field Level Likelihood for Inference of Galaxies. This work has been done by me and all these people listed here, my collaborators. So here you can take a look at the summary of this presentation, and let's go through all these steps together, starting with the problem. We can say that in the modern model of cosmology, we can describe a universe filled with dark matter, some kind of dark energy, and baryonic matter. Every time we're trying to get more and more data to see if our models can describe a universe. And we can get astonishing images as this one, which is the deepest infrared image of our universe taken by James Webb Telescope. And as cosmologists, we want to know one main question, which is, can we constrain the cosmological parameters? Can we infer the cosmological parameters with the highest accuracy and precision as possible to describe a universe? So right now, we do know how to do this in two different ways. And in one hand, we have the summary statistics. And for example, we have the power spectrum. However, we still have issues with nonlinear scales. And in this way, we can say that the power spectrum is optimal to deal with Gaussian fields, but it's suboptimal to deal with non-Gaussian ones. And then we still don't have optimal summary statistics to do parameter inference. On the other hand, we have the machine learning methods, which right now are showing really promising to do parameter inference. For example, we have the convolutional neural networks, the CNNs. But we still have a dependence of the resolution of the grid. When we are going to discretize our problem, we still have to choose the size of the cells. And then a question arises, is that an optimal way to do parameter inference? So we have a proposed solution, which is doing galaxy field level likelihood for inference. Imagine that we had a bunch of galaxies with all that information. How can we extract the cosmological parameters? They are going to translate all the information of all these galaxies in something that we call as graphs. And graphs are a natural representation of the cosmic web because they can trace all the filaments and the structures that we can observe in our galaxies. These graphs are going to feed our black box of machine learning, which are going to be the graph neural networks, or GNNs, which are pretty good to deal with regular data and which are already in permutational invariant. So we're going to measure mega matter, and it's pretty amazing because using this methodology, we have something which is really fast, and we do not have to impose any cut on scale. Previous to this work, to this present work, we have two amazing works. The first one, where Pablo and the other authors showed that they can indeed use GNNs to constrain omega matter from galaxy catalogs. They were using galaxy properties such as stellar mass, galaxy radius, metallicity, and maximum circular velocity. But unfortunately, that model is not robust. In this other amazing work, Ellen and her collaborators are showing that, indeed, they can use the graph neural networks to constrain omega matter from halo catalogs. And they are using as halo properties the velocity modulus and the positions. And as the title already says, the model is robust. But we observe galaxies, not halos, right? And that's why we have the new questions in this present work, which are, first, what are the galaxy fundamental properties to infer omega matter using a graph neural network? So, given a galaxy, we can have their velocity, their stellar mass, or color. But which are the most important parameters to do cosmology, to infer omega matter? And then the second question that we want to know is it possible to get a robust model? When we are training a machine learning model, we need to choose our data set. In this work, we have to choose the hydrodynamic simulation, so the subgrid model that we have our boxes of our galaxies, okay, to infer omega matter. And then, after training the machine learning model, we want to test it in different hydrodynamical simulations, which were run using different subgrid models, okay? So the idea is that we wanted to infer omega matter for these different simulations. But this is not an easy task, because most of times the difference in the subgrid physics is a challenge for the machine, and it's not possible to extrapolate for these different boxes, okay, for these different models. But in this work, we would like to have a machine learning model which is able to be trained only in one kind of simulation and which is able to be robust to extrapolate for other ones. And then we would like to infer omega matter. And the third question is that we want to give at least the first steps in the direction to apply all this machinery in real data. So let's talk about graphs. And what are graphs? Graphs are mathematical structures composed by nodes and edges. So we have a graph here. And for the nodes and for the edges, we have nodes and the edges attributes. In this work, our nodes are going to be our galaxies, and the node attributes are going to be their properties: velocity, stellar mass, color, and so on. And the edges are going to be the connections, the links between the one and other galaxies. And we are going to get these edges using galaxy positions. And the edge attributes are going to be properties, okay, which can keep translational and rotational symmetries, because our universe is already homogeneous and isotropic, right? More information about these edge attributes can be found in the paper. But how we can connect two galaxies, okay? How we can define the edges? Imagine that we have this other bunch of galaxies, and then we want to see if this red galaxy is connected to these other ones. The idea is we are going to grow a sphere around this red galaxy, defining a radius. We will say, okay, if these other galaxies are inside this sphere, are inside this radius that we call as R link, then we're going to connect them and set their edges. In all the machine learning models that we run in this work, we found that this R link is around 1.25 megaparsecs per h. So right now, we know what graphs are, and in this work, each one of the boxes of the hydrodynamic simulations are going to be translated into one graph. So one box, one graph, and here you can see a representation of one graph. And then it's time to talk about GNNs. Graph neural networks, or GNNs, are going to be fed with our graphs, our galaxy catalogs translated in graphs. Okay. But what are the graph neural networks? So, as always, it's a machine learning black box. But the idea here is trying to unravel why and how this works, okay? So, in our implementation, we choose to do a message passing scheme, which means that for each iteration in this method, okay, we're going to update the edge and the node attributes. That's why they are changing colors from here to here. So in our architecture, what happens is that we have a sequence of layers, okay, which are going to do this update, okay, update the values for the edge and for the nodes per time. At the end, we are going to have an updated graph, okay, with all the information corresponding to small and larger scales all together. And one more time, we are going to compress this information into some simple multi-layer perceptron, which will be responsible to obtain the posterior distribution, the mean and the standard deviation for omega matter. So that's how our GNNs works. Now it's time to talk about the CAMELS, the simulations, the dataset that we're using. So the CAMELS suite is an amazing suite that allows us different boxes for different subgrid models, different hydrodynamical simulations, okay, varying many parameters. But in all of these cases, we're going to deal with boxes which have 25 megaparsecs per h. And these parameters are the following. The first ones are the cosmological parameters, which are omega matter and sigma h, and the astrophysical ones, two related to supernova and two related to AGN. In the CAMELS suite, we have different models, different subgrid physics models. For example, we have Astrid, IllustrisTNG, SIMBA, Magneticum, and Swift Eagle. And more than only different models, we have different sets, which were important to do this work, as you are going to see in the next slides. So these different sets comprehend different kinds of how we deal with each one of these simulations. This first one is the Latin hypercube, or LH. So we have more than 1,000 simulations for each one of these different models, where we are going to vary all the time the cosmological and astrophysical parameters. So the 6 parameters here. And we call this as Latin hypercube because it's doing a Latin hypercube the way that we are going to sample in this parameter space. And then we have another set, which is the cosmic variance, RCV, which corresponds to different realizations using this fiducial model, or in other words, the same values for cosmological and astrophysical parameters, but changing the different seed that we input to run these different models. And then we have a 30 model, a 30 model or a 30 set, okay, which can call a subhalo sequence, which is nothing more, nothing less than another set of realizations of the IllustrisTNG model called SB28. Okay, but why we are defining this as a different set, okay, and a different model? Because in this case, we're going to vary not only these 6 parameters here, but we are varying 28 parameters, 5 cosmological and 23 astrophysical ones. And subhalo sequence because that's the way that we do the sample over this huge parameter space. So this is CAMELS. And right now, we're trying to say about the way that we perform this work. And as I told you, we are training a GNN using one specific suite of the CAMELS dataset. Okay, so we're going to choose the subgrid physics model that we're going to train our machine learning model. So we're doing this using this L8 set. And why we're choosing this L8 set? Because we wanna to infer omega matter in the way that we are marginalizing over all the different astrophysical parameters. So that's why we choose this L8 set. And then, after training the machine learning model, we're going to test it. And the first test is done on itself. So we are going to use the same hydrodynamic simulation, the same subgrid physics model that we choose to train our machine learning model. So we do this test in LH and CV boxes that the model has never seen before while training, okay? And because the model is tested on itself, it's supposed to work, and then we call this as a sanity check. The second test is measuring the robustness. So we're going to test our machine learning model in other hydrodynamic simulations, in other subgrid physics models. So we're going to use LH and subhalo SB boxes and CV sets as well. And then we have to say that to do this work, we made a trick. And the trick is, okay, I told you that we are marginalizing over the different astrophysical parameters, right? But more than that, in this work, we are marginalizing over different minimum thresholds for stellar mass. And how have done this? So in the training step, for each one of the boxes that we are going to use to train our machine learning model, we are replicating this, augmenting the dataset in the way that we copy a box 10 times, and then we are selecting galaxies for each one of these 10 different boxes according to a minimum value for their stellar mass. So we're starting with 1.3 10 to 8 solar masses per age, and then we go to 2.6 10 to 8, and then in this way, we are training our machine learning model and obtaining omega matter. All the tests that you are taking a look at this work are made for this specific choice in this stellar mass threshold, which is exactly in the mean of this range that we choose to train the model, okay? And then we are going to infer omega matter. It's important to say that this trick was very primordial because we wanted to have a model which is independent of this minimum stellar mass threshold in all of these different boxes. Now it's time to take a look at our best model. So let's go to our results. Our best model follows for our training set being Astrid. And then the galaxy information, which gave for us the best inference for omega matter, our best inference for our cosmology, were the galaxy 3D positions and the z component of the velocity. And then I have to say for you that we choose only one component of the velocity because remember that we wanted to have a model which gets the first steps in the direction to be used in real data. So in real data, we have only the radial velocity, which is the velocity that we measure in the line of sight, so only one component. And then that's why we are using only one component of the velocity, and for simplicity, the z component. We are going to test our machinery in different hydrodynamical simulations: Astrid, IllustrisTNG, SIMBA, Magneticum, and Swift-Eagle. Here, you can see the results for our sanity check. So our inference for the model, which was trained on Astrid and tested on Astrid. So I'm presenting for you the predictions versus the truth, and the best values follows this gray line here, which is the one-to-one correspondence, okay? And just by eye, you can see that our points follow this line. And it's important to say that our blue points here, okay, corresponds to our inference for the L8 set, and our black point here corresponds to the inference for the average over all the inference for all the CV boxes for Astrid. And okay, the results are pretty good. We can take a look at the metrics at our scores, okay? So you can see that our root mean square error is a low value. Both the R2 and the PCC, which means Pearson correlation coefficient, are closer to 1, which is as good as possible too. Our model is not biased, so our bias is low as well. Our relative error is close to, or is around 12, which is pretty low. And then we have our chi-square error, which is close to 1, and which indicates that we are able not only to well predict the mean value for our inferences, but we're able to predict pretty well the error bars together. And then this is our best model, our sanity check. So let's see the robustness. And when we tested our model on IllustrisTNG, on SIMBA, on SB28, and even on Magneticum, you can see, just by eye, that all our values are close to this one-to-one line. And if we go deep, we can see that all of our scores, all of our metrics are all pretty good. So our model is robust. And here we can highlight that it's robust and it can even work in boxes, which vary more than the cosmological and astrophysical parameters that we have, okay, that the model has seen in the training stage, okay? So we have in this subhalo sequence a huge difference in these different parameters, and even so, the model is able to do amazing predictions. Keeping an eye in your best model, we can highlight this other test in the Swift-Eagle boxes. I'm presenting for you the truth minus the inference values, arranged just by order. And because it's truth minus inference, the good results are supposed to be closer to 0. And just by eye, they are. If you take a look at the metrics, at the scores, they are all pretty good. And why I'm highlighting these results for you? It's because this Swift-Eagle is a different hydrodynamical simulation where the halos and subhalos were found using a different halo-subhalo finder, which is the Velociraptor. And our model was trained in Astrid, where their halos, subhalos were found using subfind. So even with this difference, the model is still able to do good predictions for omega matter. And then we can right now say, okay, our best model was achieved when we were using the galaxy positions and the z component of the velocity. But our model was amazing when we trained it on Astrid. What happens when we train our model in a different data set? So in IllustrisTNG and SIMBA. And in this work, we saw that when we train our model in IllustrisTNG or SIMBA, the results are not robust. So here we are taking a look at the truth minus the inference, okay, for the CV boxes, okay, of Astrid, SIMBA, Illustris, and Magneticum for a model that was trained on Illustris and trained on SIMBA. And just by eye, we're not following this 0 line in all the cases. If you take a look at the scores, they are terrible. And then we can say, okay, a model which was trained on IllustrisTNG or SIMBA does not give for us a model which is robust, which can extrapolate their predictions for different hydrodynamical simulations. And the question that arises is why the model trained on Astrid is so good. And we have two different ways to try to explain this reason. And the first one is related to the number of galaxies that we have in these L8 data, in these L8 sets, okay, for Astrid, SIMBA, Illustris, and all the others. And then we can say that in the case of Astrid, the model that we trained it in using Astrid, we see that we have boxes which have from 40 galaxies to more than 1,000. And this does not happen in SIMBA and Illustris. This range of number of galaxies per catalog is much narrower. And then we can say that, okay, one of the reasons why the model trained on Astrid is better is because we consider a broader variation in the number of galaxies. The second possible explanation is that Astrid produces a larger variation in some galaxy properties, which gives, given the L8 set, which gives for the model a data set which is able to extrapolate more because the model has already seen galaxies which has lots of different properties and lots of different things. So that's why Astrid is so good. And then, even having this amazing model, we tried to go a bit further. We tried to improve our model. And we have done this, still keeping an eye using the training set as a Astrid suite, still using galaxy information, 3D positions, and the Z component of the velocity, but we added the stellar mass. And then we are performing the tests in the other hydrodynamical simulations. In this case, we have our sense check. And when we took a look at these results, we said, okay, the results are amazing. Just by eye, we are closer to this one-to-one line here. And then we go further and try to take a look at the scores. Almost all of them have improved. So we achieved a more precise model. But we achieved a precise model at the cost that we lose robustness. When we tested our model on IllustrisTNG, SIMBA, SB28, or even Magneticum, the idea is that just by eye, we can see that our predictions are not following this one-to-one line anymore, at least for IllustrisTNG, SIMBA, and SB28. All the scores are bad, okay? This does not happen for Magneticum, but generally speaking, we can say that the model is not robust anymore. And here, it's important that when we included stellar mass, we are closer to the difference in the subgrid physics for these different hydrodynamical simulations, for these different hydrodynamical models. So the idea is keeping just the galaxy positions and velocities. We can have a model which is able to extrapolate and which can overcome this difference in the subgrid physics behind all these models. And because we saw that for do cosmology using graph neural networks, we only need galaxy positions and galaxy velocities, we have to say, okay, where does the information come from? And then we perform the test, trying to see the importance of only the positions or only the velocities. So we measure the importance of only the positions of the galaxies, building a GNN without node information, and we measure the importance only using the galaxy velocities, building a deep set. You can find more details about these two different architectures in the paper, but the idea is take a look at the results, at the implications of the results. And then, when we perform a sense check, even only using the galaxy positions or the galaxy velocities in the model trained on Astrid and tested on Astrid, we can clearly see that the error bars increased, okay? All the scores are bad as well. And when we try to see the robustness, we saw that the model breaks down. Apart from the fact that the error bars are larger, we can see that we're not following this one-to-one line anymore. And then we conclude that to do cosmology, to infer omega matter with graph neural networks, we need both. We need galaxy positions and velocities. At the end, we can try to ask the question, can we apply this machinery to real data? So I told you at the beginning, we're trying to get our first steps in order to apply this machinery in real data. And the fact that we have a model which is robust is the first step. But we have a lot of problems that we have to overcome as well. And these are related to the next steps of this work. The first one is that to see if the model is robust to changes in supersymmetrical covariance, because we have trained our machinery in boxes which has only 25 megaparsecs per h. And then, is our model able to do inferences in small subsamples of bigger boxes? Because when we have bigger boxes like this, we have different modes that can be coupled. And then we have to see if this coupled in these modes can influentiate a lot or not our inferences in a machine learning model which was trained only using smaller boxes. And we have a first test in the paper, and more details are given there, but this first test already says that, yeah, we can do this, but we have to overcome something related to the periodic boundary conditions. Again, more details in the paper. The other thing that we have to think about is that we have errors in the measurements in the peculiar velocities. Unfortunately, we cannot have the peculiar velocities with the highest accuracy and precision as possible. So we have to take these errors in these measurements into account. We have to take care of selection effects, because in all these boxes, in all these hydrodynamic simulations, we have all the kinds of galaxies that we can dream about. But in the real world, it doesn't happen all the time. So sometimes we can only observe, for instance, red galaxies or any other kind of galaxies, and then we have to take these selection effects into account too. So let's talk about our answers in this work, the takeaway messages. We can say that the most important galaxy properties for the graph neural networks to constrain omega matter to do cosmology are the galaxy positions and the galaxy velocities, and we saw this using the Z component. In this work, we were able to constrain omega matter for 5 hydrodynamical simulations: Astrid, SIMBA, IllustrisTNG, SB28, Magneticum, and Swift-Eagle. In all of the results, we achieved relative errors which are around 10 or 11%, okay, which is a pretty low value for all of these cases. And then we achieved a chi-square, which is pretty close to 1 in all the cases too, indicating that we can measure the mean and the error bars for omega matter. And it's important to say that this is the first time that we have a model, a GNN model, that works only using galaxy catalogs, that is able to extrapolate among this huge different number of hydrodynamical simulations. And we are giving the first steps to apply this machinery in real data. And we would like to do these following steps in our next work. So, PS, postscript right now. Together with this work, we have this other amazing work, which is a companion paper called An Universal Equation to Predict Omega Matter from Halo and Galaxy Catalogs. In this paper, Helen is showing that we can use something that we can call, which is another machine learning method called symbolic regression, which is applied for GNNs to constrain omega matter from Halo catalogs. The method was trained on Halo catalogs. And in this work, Helen is showing that she can extrapolate for different Halo catalogs and even for Galaxy catalogs. So the object properties that she's using are the velocity modulus in the Halo positions. And then this work is a step in the direction for a physical interpretation behind the success of the GNNs. And the model is robust. As I told you, this is working for different Halo catalogs from different antibody simulations, and even more for Galaxy catalogs too. So that's it. Take a look at that paper too. And then I have to thank you for your attention. And if you have any questions, any comments, if you want to just chat about this work, please let me know. Thanks.